It's a great pleasure to have Wei Li speaking to us, technically from the Academy in Beijing, but she's in Zurich at the moment. So thank you for joining us.
Thank you very much.
And she's going to tell us about Quiver Yangian from crystal melting. And we can take questions as we go along as well. She's happy to do that.
Okay, thank you very much. Good afternoon and good morning. So the title of my talk is Quiver Yangian from crystal melting, and I'll explain what this means in a moment. So this work is mainly based on this recent paper I wrote with Masahito Yamazaki, and I'll also explain. I'll also I'll use the mouse here. I'll also talk about some related work that I did with Pietro Longhi. So this is try to solve the same problem with a different approach, the so-called gluing construction. And this gluing construction was also developed together with Matthias Gabriel and Cheng Peng in this earlier paper. And we're also excuse me, can you see the end of this with this four at the very bottom with the 4 pages, even when I move the mouse? Sorry, you're muted.
We can see the page number at the bottom, half of the page number, so I think everything is visible. The bottom line is a reference to it has higher spins and Yangian symmetries, and it's Matthias Gabriel Gopar and Cheng Peng.
Right. So this is also uses earlier paper with Matthias Gabriel, Rajesh Kumar, and Peng Cheng. So the bigger context of this work is the following. So the main question we want to ask is what is the algebraic structure underlying the BPI sector of 4D angle 2 gauge theory? So the element of this algebra is the states in the BPI sector, and the multiplication is given by the fusion of 2 BPI states into a bigger BPI state. So this BPI algebra is the analog of the Carré algebra of the Carré primaries in the 2D angle 2 CFT. So so the reason we're interested in this BPS algebra is it contains some very robust information about the theory, and it should be invariant and certain duality transformations. So namely the 2 theories that are related by some duality transformations should have the same BPS algebra. Also naturally it will contain many aspects of the theory, for example, the threshold corrections, the BPS counting, and the word crossing, etc. Right, so I would like to say a few words about the history of this BPS algebras. So it started by the work of Harvey Moore in 1996. So they focused on the single particle BPS sector of the 4D angle 2 gauge theory, and namely they consider the fusion of two single particle BPS states. So the mathematical structure of the resulting algebra is not very clear. So in some cases, it's a Lie algebra. So, and then much later in around 2010, 2008, Kantarich Soibinen started asked the same question, but included also the multi-particle BPS states. So they look at the entire BPS Hilbert space, and also what is the BPS algebra of the theory. So their formulation. So once you do this, your BPS algebra has some more generic mathematical structure in terms of this cohomological Hall algebra, the coha. So and then so this is only considering the fusion process, but from the physics point of view, it's also natural to include the decaying process, namely how a bigger BPS particle decay into two smaller ones. So mathematically, this corresponds to enhancing your algebra with some additional coproduct structure. So namely, we want to consider the dreamfield double of the cohort. So this is shown to have the alpha and Yangian algebra structure. So this alpha and Yangian algebra formulation is going to be the formulation that we're going to focus today. And it is also shown to be, in general, be isomorphic to the universal enveloping algebra of some W algebra, and which W algebra more familiar to us as a physicist. So this is so I'm going to be very fast in this introduction, but many terms and the details I'm going to explain later. So this is the setup. So we're going to consider the type 2A string in non-compact toric Calabi-Yau threefold. So the simple example is C3. So this toric Calabi-Yau threefold is just is a T2 cross R fibration over the R3 basis. So the information of this toric Calabi-Yau is in this toric diagram. So this shows where the fibers degenerate, like along these lines. So this is the simplest one. And so all the other ones can be obtained by just gluing this, what is this, into infinite many other examples. So this the next simplest one. You can glue two to obtain this result quantifold. And in general, there are two classes. One is those without the compact four cycles. Then correspondingly, that means the toric diagram has no compact loops, such as this, and those with compact four cycle. So that means this toric diagram has a closed loop here. So this is the simplest one, and then and then some representative in these two classes. So the resulting theory is four-dimensional n = 2 gauge theory. So we're interested in how to build a BPS algebra for this theory. So so there's an effective description of the BPS sector in terms of supersymmetric quantum Quiver quantum mechanics. So this Quiver quantum mechanics, the information is just contained in a pair of a Quiver and superpotential here. So namely, the BPS algebra can either be labeled by the toric data or by this Quiver and superpotential pair. So from the toric data to the from the this toric diagram to the Quiver data, so there's a one-to-many map. Then different Quiver correspond to the same torics, so they're related by several duality. But we're going to so mostly we're going to ignore this subtlety here today. Right, so let's look at the simplest one, the C3. So this is a toric diagram, and the equivalent Quiver data is this one. So this the Quiver theory has only one gauge group and three adjoint here. So this is just n = 4 super Yangian, and this is the written in the n=1 language. This is the superpotential. So starting from this one, you can build you can construct a set of BPS states. So it turns out in this case it's labeled by the set of plane partitions, and we also know the result of BPS algebra in this case, and this is given by this algebra called alpha Yangian GL1, which is the building block of this entire construction today. So I'm going to explain in much more detail how this alpha Yangian GL1 looks like. But right now, this is enough for now that this is the building block, and also it is universally enveloping. It's isomorphic to the universally enveloping algebra of the W1 plus infinity algebra. So we know how this BPS algebra acts on the set of plane partitions. And the more important thing for us today is that suppose we didn't know about this algebra, we just started from the set of the plane partitions, and we have some under some certain ansatz, and we can basically bootstrap this BPS algebra from the representation. So we asked the BPS algebra to act on this set of plane partitions in certain ways, and then the constraints are actually enough for us to solve the entire algebra, as I will explain later. So, so how to generalize this the simplicity case to the general Calabi-Yau? So, if you look at this toric diagram, you see that they are all they can all obtained by gluing this individual trivalent diagrams here. So then one most natural idea is that the resulting BP algebra can also obtain by gluing this building block, the upper Yangian GL1, by some using some additional gluing operator that correspond to this internal leg, and then demand the algebra to have some certain properties and obtain the final BPS algebra. So the internal legs correspond to the additional gluing operators. So they should transform as the bimodule with respect to the two upper Yangian GL1 that at the two ends of this internal leg. So it's not clear what the whether for the faces there should be additional operators, because we haven't reached too far from this gluing using this gluing construction. So we managed to do the simplest cases with two vertices. And so, but there's some, without getting the entire algebra, people has also tried to get some information just using this gluing construction in the W algebra basis. So the general, the guess is that they should all fall into the class of alpha Yangian of this superalgebra GL n/m, but it's not clear how to push this gluing construction to the general Calabi-Yau. So to proceed, let's go back to the CC case to see whether this offers some other hint as to how to generalize to the general Calabi-Yau, general toric Calabi-Yau. So so if you start from the Quiver description, see that the Quiver description allows you to build the entire set of BPS states from which you can bootstrap the BPS algebra in this case. So for the general toric Calabi-Yau, we also know how to write down the corresponding Quiver quantum mechanics. And also people also know how to build the entire BPS set of BPS states, starting from this pair of the Quiver and superpotential. So in this case, the set of BPS states can be described by certain colored crystals. So this colored crystal are the generalized set of plane partition in two directions. So one is that now the atom can have two colors, which correspond to the different vertices in the Quiver diagram. For example, this guy will have 2 colors, and this will have 3 colors. Also, the shape of crystal will also wouldn't be have the same shape as a plane partition. So the shape will be determined by the information in this Quiver the superpotential pair. So the result of this talk is to explain how to bootstrap the BPS algebra for general toric Calabi-Yau, starting from the information contained in the Quiver quantum mechanics. Yeah, so this is the summary of the construction. So starting from non-compact Calabi-Yau threefold, we consider the BPS sector of the deep-brain system of type 2A string. And write down the Quiver and superpotential pair, and use that to construct the set of color crystals, from which we can bootstrap this BPS Quiver Yangian. So,
sorry, Willie, why does it have to be non-compact?
There's no non-compact Calabi-Yau threefold. So, except for the
there are super Calabi-Yaus that are I mean CP34 there, which has
so right, okay. So first, I don't know of any non-trivial compact Calabi-Yau. Also, in this case, we wanted to study the 4D gauge theory. If it's compact space, then the 4D theory will have gravity. Then the problem will be much more complicated. So we want to study we want to start from the gauge theory. So that's why we only use the non-compact space. The 60 space we wanted to have we want to have a 4D gauge theory instead of 4D gravity. Yeah, thank you for the question. So we got this BPS algebra starting from using this bootstrap method, but in the end, we just get a prescription that that you can write down this Quiver Yangian just directly from the from this Quiver data. So this prescription fits in one page. It's actually very simple. If you just want to result, you don't even need to focus. Sorry. You don't even need to focus on the talk. You can just wait until the end and to see that one page prescription starting from the Quiver data. So so compared to other approaches, this is gives you very explicit algebra relations. And also, this is the same procedure applies to any toric Calabi-Yau threefold. So at the very end of the talk, I will also mention some applications. So this Quiver Yangian allows truncations, which could give us new rational vortex operator algebras. And also related to some other interesting system that has been studied in recent years. For example, this vortex VOA and the gluing from those corner VOAs, and also this spec instanton and generalized AGT. So I'll explain this after I study the Quiver Yangian. Okay, so I finished the introduction. So now let me basically tell this story again in more detail. So the setup is we look at the type 2A string compacted by non-compact toric Calabi-Yau threefold. So this is you can think of this toric Calabi-Yau in terms of a T2 cross R fiber over R3 base. And the information of this toric Calabi-Yau can be contained in this toric diagram here. So this is some examples here. So the deep bound state here. So we're going to consider the bound state of this. In general, it's D64, D2, D0 bound brains wrapping the holomorphic 6420 cycles of this Calabi-Yau. So we consider the half BPI states in this theory with this given deep charge. So the question is how to describe these states. So so we can only so we're going to focus on the case where you have only one D6. So one D6 wrapping the entire Calabi-Yau. And so to construct this algebra, we don't need to have any D4 brane. So as I'll explain later, having non-zero D4 brane just correspond to the truncation of this algebra. So to build the algebra without the truncation first, we just need one D6 and then some arbitrary number of D2 and D0. So the BPS states to study this BPS state, you can look at the low energy effective theory on the bound states. So in particular, you can reduce this 4D theory all the way down to one dimension. So that's the N=4 quantum Quiver quantum mechanics. So the entire information is just in this Quiver and superpotential pair. So the Quiver has two informations. One is a set of vertices. So each vertex corresponds to a gauge group, and the link, the arrows between the vertices represent the bifundamentals that transform and with these two gauge groups and the superpotential. So the useful information, the information we need today is that we can repackage this Quiver and superpotential pair in terms of a periodic Quiver. So namely, we have a choice of drawing this Quiver on a T2. And the superpotential just given by the phases of this periodic Quiver. So in most of the talk today, when we say Quiver superpotential pair, we equivalently mean the periodic Quiver here. So for example, for the C3 here, this Quiver, and at the bottom is the superpotential, and you see that you can also repackage this information into this periodic Quiver. So for any toric data, you can also obtain the information of the periodic Quiver using this technique developed by Hanani and collaborators called brain tiling. So this is a very powerful technique. So also quite interesting and powerful. But we're not going to explain this in detail. We just we'll just use the result here. So, for example, this periodic Quiver that I mentioned already, and this for the corner you look like this, and this is more complicated. This P2 case here. Now, starting from the Quiver quantum mechanics, you can use that to describe the set of BPS states. So, so basically, we want to focus on the T2 invariant states of this Quiver quantum mechanics. So it turns out there's some derivation here. So that in the end, you can see that it's given by a certain three-dimensional crystals whose atoms has different colors, and each color corresponds to each gauge group in your Quiver quantum mechanics. So there's a one-to-one correspondence which a particular Quiver configuration with a particular D-brane bound state. So here I should have put, in most part of my talk, this D4 will have, there's no D4 brane here. So this is an example of a BPS crystal for a particular Calabi-Yau here. So it's labeled, here has the three colors as this white, black, gray. So it corresponds to three different gauge groups. So each atom here carries a certain combination of the D2, D0 charge. So here's some terminology here. So in this old literature of the crystal melting papers, so they started with the full crystal. I mean, it's covered. So you first grow all the entire crystal, and then starting from the origin, you melted away a piece. So they call this piece molten crystal. So this molten crystal is the BPS state that I want to consider. So for example, this will have the will give a term of so there are 4 Q1 and 3 Q2 and 4. Sorry, should be 4 here, 4 black 1. So the point that each crystal configuration corresponds to a particular BPS state with a particular combination of the D2 D0 charge. Yeah. So starting from the periodic quiver, the way to construct, there's also a very streamlined way to construct your BPS crystal. So this is supposed to be drawing on the, it's supposed to be a periodic quiver drawing on the plane. And this is the fundamental domain. So I can choose I mean, I'm only drawing this part, but it's supposed to be covered the entire 2D surface. And so you start from an arbitrary vertex and choose that to be the origin. So the atom in your crystal corresponds to a path from your origin. So there's this rule called melting rule that if some crystal is not there already in the crystal, any crystal that's that connected by some error from that atom shouldn't be in the crystal. I mean, this is just saying, for example, in the plane partition, and you cannot have some atom floating in the air. And this equivalence path just means that starting, you can reach a particular atom from by multiple different paths starting from the origin. So this suggests that we give the coordinate of the atom can be labeled by the sum over this parameters starting from the origin, and our global symmetry of the gauge theory also suggests that we need this loop constraint. That so around each loop, the sum of the charge should be 0, and also the vortex constraint here by the gauge symmetry. So any questions here? I think I'm doing okay in time now. So if there's no question, I'm going to move to the simple case, the CC case. So the CC case here, the quiver and superpotential pair is this, and I already showed what the periodic quiver looks like. And so in this simplest case, the loop constraint and vortex constraint are the same. It's just the sum over each 1, 2, 3 give you 0. So also, so if you start from this periodic quiver and draw the 3D crystal, it will have the shape of the plane partition. So here is this plane partition, and I wrote down the generating function here. This is my quantum function. So we're not going to use it today, but in general, you can, what I showed earlier, this is just the plane partition in the vacuum module, meaning that you start from the empty room and then stack boxes. So, but we can also study the ground state of a non-trivial module. So a non-trivial module is labeled by 3 Yang diagrams as the asymptotic direction of this 3 direction. So once you fix the 3 Yang diagram, you go to the go inside the room and then look at the minimal configuration. So that will be the ground state of this particular module. And then the excited states will be adding more boxes on this on the ground state. So this is the building block of our or the starting point of our BPS algebra here, called alpha Yangian GL1. So it is an associative algebra with 3 families of generator here. So this psi here is a Cartan, and E is a racing operator, and F is the lowering operator. And it has this complicated looking defining relations. So it has 2 parameters, sigma 3 and sigma 2. And also we need some initial conditions and set relations. So, I mean, if you look at like math too, it might be helpful to know that this is actually isomorphic to the universal enveloping algebra of the W1 plus infinity. So this so the double algebra is just a Virasoro algebra with some additional higher spin conserved currents here. And the W1 plus infinity algebra is a double algebra with a particular spectrum. So the spectrum is we have one primary field per spin, starting from spin 1 and all the way to infinity. So the structure of this algebra is once you fix this spectrum, the structure is very tight. So the OP is completely fixed, and there are only two parameters. One is the central charge, one is the lowest coefficient from spin 3 fills into spin 4. So to see roughly how this isomorphism maps, so it's a map. So here I write down all the modes of the W1 plus infinity. So this is vertical direction is the spin from 1 all the way to infinity, and horizontal is the mode. So this vertical line is a 0 mode, and this the racing operator with level.
We can't see your mouse, I think.
Now we can.
No, which may. So I'm not sure what you're pointing to.
I can see my mouse, but oh, sorry. I thought the mouse is visible, but I don't know how to. I don't know how to turn on the I mean, because the mouse is from the laptop and I'm sharing from the iPad. I don't know how to turn on the.
Well, if you tell.
Maybe I draw here.
Yeah, that would help. Yeah.
So this line is a 0 mode.
That's much better. Thank you.
Yeah. Sorry. So this line is the mode is -1 number. This is the +1. Okay. No. So roughly speaking, the isomorphic maps. So remember we said for the alpha Yangian we have 3 family of generators: the Cartan and the racing operator and the lowering operator. So roughly speaking, the isomorphism is all the 0 modes in the W algebra here map to the Cartan of the alpha Yangian, and here all the E mode map to the -1 mode of the W algebra, and the F mode, the lowering operator, map to the +1 mode here. And then using the multiplication, you can generate other modes here. I mean, here all the E's multiplying give you all these other modes.
And where does the co-product come from?
I'm not going to. I mean the co-product. Yeah, I mean you just let the. So there's so the dictionary. Yeah, I don't remember on top of my head how the. So we discussed this mapping just so we find this mapping directly in terms of mode, and then checked up to so as you can see earlier. Because there's only 2 parameters, and so once you know the OP coefficient from the 3 to 4, all the higher ones you know. So that means when you check this, you only need to check up to spin 4. So what we did is we just map the mode up to spin 4, and then find the dictionary between this 2 Yangian parameter with this 2. I mean, this should be this lambda or equivalent C334, the correspondence between these 2 parameters. Yeah. So then, but so in our paper we didn't check the co-product. I think the Prochaska has some discussion in the, but he also claimed there's some problem, but I forgot what exactly the, yeah. So maybe I can try to answer you later. But on top of my head, I don't remember how the, I mean, we didn't, in our paper, we didn't check the co-product. Right. So there's a very useful triangle relating the alpha Yangian GL1 and W symmetry and the plane partition here. So in the sense that from the alpha Yangian GL1, the plane partition is the natural representation. And also from this, you can also, from the plane partition, you can also, it's actually very useful to use a plane partition to study the representation of the double symmetry. Here. So now we go back to this formation of the alpha Yangian GL1, this horrible mess in this page. So to study to connect to the plane partition, the representation of the BPI states here, is actually neither the formulation of the W algebra nor the alpha Yangian GL1 in terms of modes. Neither of these two formulations are very useful in studying, very convenient to study this the representation. So so it turns out that it's better to use yet another formulation of this alpha Yangian GL1. So the trick is to group this generator into 3 families. So this is similar to the relation of the modes and the fields in a CFT. And then we reparameterize this sigma 2, sigma 3 into a triplet of the 3 parameters, the H1, H2, H3, and this sum equal sum to 0. Remember, this is reminds of this loop constraint that we mentioned earlier. And also, this is more suitable for this because of the intrinsic S3 symmetry for the plane partition. So now we can translate the algebra relation in terms of mode into the relation in terms of these 3 fields. So we just focus on these 3 relations. So these 3 relations here, I got translate into the relations here. So in the process, we introduce this cubic rational functions. So this is an invariant under the permutation of the 3 H parameters. So and then you can continue and also translate all these other relations. So in the end, this is all the relations, defining relations here. Here. So remember how this relations here. So you see this the important ingredients is this 5-3 function, this cubic rational function here. So with this formulation, we can use that to the formulation of the alpha Yangian GL1 in terms of fields to study its representation on the plane partition. So it's written here. So so here are the essential features of this representation. So each plane partition is the eigenstate of this family of catons here. And so this box, this means this square means a box inside the plane partition. So each box contributes a factor here. And so it's shifted, is this Wi-Fi function shifted by the coordinate. So, and the coordinate functions defined here. And then once you get this eigenfunction of for each plane partition, the action of the E and F, they're just entirely controlled by this the eigenfunction here. So this should be a big phi and big phi here. So so the pole of this phi function encodes the position of this the action of the E for adding. So the E can, starting from a plane partition, the E operator add a box in all the allowed places, and the F can remove a box in all the allowed places. So the upshot is that this this phi function encode the position of where you can add the box or remove the box. So so the point is that you should be able to use this E function starting from the vacuum. You should be able to build the entire crystal. And you don't want to do this by hand. You're supposed to put this into the computer. And it should know automatically by looking at this eigenvalue function, where are the allowed poles.
So does psi control the shape of the crystal in the end? If I take some large limit, the limit of a large number of boxes?
Yeah, true. Yes, yes. I mean, there are two aspects. The shape of the crystal is fixed by your Quiver data. So this is just another way to encode the not just the shape, also, yeah, I mean, this is a way to encode the microscopic shape of any particular crystal. Any crystal, it doesn't need to be the entire crystal. It can be just a corner or with some, or I mean, in this case, just encode the information of any plane partition.
But the shape of the crystal determines where I can add a new box. So,
yes, so that's the information is given by the pole here. So see here, you're looking at, I mean, the coefficient here is the residue, sorry. So the coefficient here is, you are looking at the residue of this pole here.
Oh, I see, okay.
So, I mean, this is supposed to be totally automatic. You should be able to put it in a computer. So you start from any states, and then, or in particular, start from the vacuum. You just apply the E here iteratively, and then it's supposed to generate the entire plane partition. Or you start from any plane partition and then apply the F iteratively. Is supposed to annihilate after certain steps. So we will. I mean, this is very very smart system. So we want to generalize this. So the point is that when you add, so each plane partition has its own phi function, the eigenvalue function. So when you add more boxes, you see it's a product of the boxes. So when you add boxes, you can get more factors. And the new factors should remove the old pole. I mean, you only want the pole to appear at the surface of the crystal. I mean, the pole should either be a place where you can add a new box. Should either you add a new box, for example here, or you can remove this one. So all the poles have to be on the surface, either immediately outside or immediately below the surface here. So the important point is that the phi can only have poles near the surface of the crystal. So yeah, I think I'll give up. So this is just an example to show how this works by starting from the crystal and build this phi function iteratively. And you can see that for the vacuum, this function here is a pole at the 0. So that means that you can add a box at the 0 here. And so, I mean, each pole has just one meaning. So this z equal to 0 is the adding pole for E. And then you look at the state with just this one atom at the origin. So now this one has 3 poles here. So the that 0 pole that corresponds to the pole where you can remove this existing box. So the state is just has this one box at the corner of the room. So z equal to 0 is a removing pole, and there are 3 adding poles. So that corresponds to the direction where you can add the next 3. So later, I mean, this is just to show that when you add the next one, the removing pole got cancelled by this contribution from the new atom. So so as this just to show that as you add more and more boxes, all the poles get pushed to the boundary of the crystal. Yeah, okay, so this is just a summary of what I just said. So in the process, we needed this loop constraint, the H1 plus H2 plus H3 equal to 0. So any questions before I move to the general Calabi-Yau? So I'll just use the simplest one of the simplest case for the this Calabi-Yau here to explain the construction. So this is given by this toric data and gives we translate into the Quiver and superpotential pair, and using that we can write it in terms of this periodic Quiver, and it has this constraint. So the shape for general, so this is for z equal to 2. For the general n here, it actually has I chose this so that I can just use the picture of the plane partition here. I don't know how to draw a multicolor plane partition. So I started from a plane partition here. So I'll just color here on the spot. So this guy here has n colors. So the coloring scheme is that you have 3 directions. So you're starting from, so we color them by 1, 2. So let's do an example with 3 colors. So the very first one I color, the one in the bottom you color with a 1, and then in this direction you just add one color, one number in the colors. So 1, 2, 3, 1, 2, 3 along this direction. This direction is in the opposite direction. So 1, 3, 2, 1, 3, 2, and then along this direction the number doesn't change. So for example, 1, 3, 2, 1, 3, and just 1, 3, 2, 3, 2, 2. So vertically, it's the same color here. Yeah, sorry that the color is not very visible here. So this is the summary of how the action of how the upper Yangian G1 acts on the plane partition. So this just a summary. So the main feature, as I showed earlier, is that with this construction, in particular, this function here, the poles are always pushed to the surface of the plane partition. So this is what we want to realize. So we want to imitate for this new crystal or new quiver. We want to imitate this imitate the action on this colored plane partition. So what we want to realize is also that we want to have it automatically that all the poles are pushed to the surface of the two colored plane partition. So so this is just a natural guess. So this is the here. This is the alpha Yangian G1 here, and this is our new Quiver Yangian. So before we have a 3 family of generators. So now for each color, we have a family of 3 generators. So for each color, we have Katan and the racing operator and the lowering operator. so the racing operator labeled by A only as the atom with the color A, and so this psi A. So this is the part of the eigenvalue function for the color A. But the important point is that all the atoms of all the color contribute to this psi A here. So meaning that there's some relative charge function. So any atom of any color, any B, contribute to A. And so, I mean, this is just the only complication here. And all the other structures are just natural generalization here. Any questions here?
May I ask a question?
Yes, please.
So is this Quiver Yangian like some affine Yangian of GLN or some known algebra?
Yeah, for this simplest cases, this is I'm going to explain more. So for this toric diagram, this the result is the affine Yangian of GLN.
Okay,
but, it
so
can be
that's just the GLN.
It can be more general. This is the one of the simplest cases.
Okay, thank you.
So this procedure, what I explained here, applies to any toric Calabi-Yau, in particular those with compact force cycles. Right. So okay. So this is just what I just said earlier, the summary of the ansatz for how the Quiver Yangian should act on this color crystal. So so this K here is a particular colored crystal state. So it should be the eigenstate of all the katon for all colors, the katons of all colors. So the position. So this box is B is means the atom with color B. So each atom is encoded again by this by this coordinate function, which is just a generalization from the plane from the affine Yangian. So it's just a sum of all the charges along the path, and then each atom contribute a vector here. So the point is that we want to fix this relative charge function, meaning how what's the contribution of a color B to the charge function from the color of the color A. So we want to fix it in such a way that because the action of the raising operator and lowering operator are completely controlled by the final function. So we wanted to fix this relative charge function in such a way that this pole of the precise encode the position of where you can add the atom A with color A, and where you can remove them. And in particular, this should all be automatic. Okay. So this is just reminding you what's the essential feature from the action of affine Yangian G1 on the plane partition. So there, the essential feature is this Wi-Fi function. This is so you see that it has three factors in the upstairs and down three factors downstairs. So this three is actually you can think of this as the charges of the three arrows pointing in, and then three arrows pointing out. And we needed this loop constraint here. And so the generalization here is that the relative charge function, the natural generalization is this guy here. So the contribution from the B to A is given by this rational function. So for each arrows that's going from B to A, it give a factor downstairs. And for each arrows that going backwards from B to A, from A to B, they give another factors here. So this is chosen such that this cancellation of the factors inside your phi function happens, so that all the poles get pushed to the surface of the crystal. And so I think I'm running badly out of time, so I'll skip this this detailed derivation of these examples. But this is just to show that it works, that all the poles has a meaning, and you only have poles at the surface of the crystal. So this is a summary of this action. So now we know what kind of actions we want from our Quiver Yangian on the set of crystals. We want this Yangian to automatically create the crystal starting from the atom from the vacuum, and also to annihilate it automatically. So now, how do we get from this the information of the action on the crystal to how do we get the algebraic relation of the algebra itself? So now we go back. So how do we get the algebras from the action? So if you look at the action of the Yangian G1 on the plane partition, you see that the main ingredients in this chart function is given by this. There's only one function here, the last phi3, and then the phi3 appears in the defining relation here. So it can be summarized in this graph here. So the natural generalization is this. So now we have a multiple family for generators here, and so connecting them, they are just connected by this relative charge function here. And also we can it's possible that before for the alpha Yangian G1, all of them bosonic generators. So now we can also have fermionic generators here. So labeled by here. So the statistics of the generators, they can also be fixed by the Quiver data. And finally, if you want to translate back to the modes, you just starting from here. So this is some rational function here. This is a relation in terms of field. So this is some rational function with some factors here. So to translate into the modes, you just move the denominator to the other side and expand. And this, you can get the relations in terms of mode here. So this answered the question that Ridong asked earlier. So for all the non-compact Calabi-Yau, so we show that it all falls into these classes. They're all alpha Yangian for GLN/M. So for the non-compact Calabi-Yau with a compact 4 cycle, so our Yangians seem to be the new algebras. So now I'll summarize. So so the result of this work is that so we consider the BPS sector of the deep brain system of type 2A string in non-compact Calabi-Yau threefold, and we give a prescription on how to construct the BPS algebra. So the data we use is this Quiver data, the Quiver and the superpotential data that you can get from the toric data. So from there, you can write down immediately the chart function and also the statistics of the operators here. So this is just a prescription in this fits into one box, and so this is the final prescription on how to write down this algebra. And so most of part of my talk is explained how we find this prescription is by bootstrapping from the representation of this algebra, which is the set of BPS states. So this the representation of colored crystals you can build from the periodic Quiver. So as I was saying that this approach gives you explicit algebraic relations. And it's just one procedure that applies to all the non-compact toric Calabi-Yaus. So for the future directions, so first it would be interesting to go back to the gluing construction to see whether we can use this result to help us to also finish the gluing construction to see whether we can make it work for an arbitrary toric Calabi-Yau. And also it'd be interesting to translate to W basis. And also, and then finally and also to study some non-vacuum module of the algebra. So to bootstrap the algebra, we only needed a vacuum module. But if you want to study other types of, there are other types of BPS bound states. For example, those with open BPS states that those you need non-vacuum modules. And finally, it's interesting to study the truncation of the algebra. So those will correspond to the non-zero D4 charges. And the truncation will also produce the rational new family of rational UAs. And also this will relate to other systems. But I think I'm running over time, so I'll end here and I'll answer questions first.
Okay, thank you very much for your talk, Willie. Are there questions?
Yeah.
Bernard.
So first, thank you too. When you went over from the W algebra parameters, W infinity, sigma 2 to sigma 3, to the H's, you had some permutation symmetry of 3 objects, which you don't see in the W algebra itself because everything is symmetric. So what is this permutation symmetry? Is that some kind of duality, or what is its meaning?
So this permutation symmetry, let me see the pages. Right, over here. So the permutation symmetry is known to also exist in the W algebra, but it's not very apparent. So it comes from here. So the real parameterization of the W algebra here is in this central charge and the OP coefficient. But it's not, so this OP coefficient 334, it fixes all the OP coefficient of higher OPs. But when you write the algebra itself, it's not, I mean, this is not a convenient choice. Its convenient choice is the C lambda, this truth coupling, or the NK in the WNK parameter. So, but the real parameter is the C and C334. But when you want to translate to the C lambda and K, you want to solve this pair into this other pairs. So when you solve this, there's some cubic equations. Also, there's some flip of signs. So when you solve from this pair of parameters, for example, in terms of the N and K, for one pair of C and C334, you get 6 solutions of different N and K. So those will correspond to the 6 different images of the S3 permutation.
So remind me, what are N and K here?
Sorry, so this is in a formulation of the coset formulation of the W1 plus infinity algebra. So this one doesn't have this one doesn't have the spin 1, but it's easy to decouple this 1 here, or just to tensor another U1 here. So this is just sorry, SUN plus SUN K1.
Okay.
SUN 1 plus K. Yeah. Just a coset.
Okay.
To stick. Yeah. Yeah. So yeah, one reason why this alpha Yangian GL1 is better suited for this describing the representation in terms of plane partitions, also that it makes this intrinsic S3 permutation symmetry more manifest. So this is actually very helpful when describing the representation, even for the W algebra itself.
So is there a level rank symmetry?
Yes. So we have S3 symmetry here. It has 6 images. So suppose you start from this pair of C334. When you solve for this pair of NK, you get 6 images.
Yes.
So 3 of them correspond to the. So if you want to solve for the pair of C lambda, you get 3 images. But this lambda also has so one pair of C and lambda correspond to 2 pairs of N and K. But that's not the anyhow. Inside the 6 images, there's a map of the that's the level rank duality here.
Yeah, thank you.
Another question from anyone?
May I ask?
Yes, of course. Go ahead.
So the quiver used here, is it related to the so-called BPS quiver in the gauge theory context?
I think the same quiver.
Oh, okay. Well, and I'm also a little curious that, well, in the usual context of AGT, the Yangian of GLN appears in the, well, when we obifolding the omega background, but here it just appears in the, well, usual like toric Calabi-Yau context. Do you think there's a duality?
I think it's probably related. Actually, I mean, this for me, maybe I have a chance to mention the relation to this generalized AGT story here. So, sorry, maybe I need to explain the truncation here.
Okay. Could you explain it a little?
Yeah, sorry. So can you see this page now?
Yes.
So this, let me draw here. So, so this alpha Yangian GL1 is equivalent to the EVA of the W1 plus infinity. So this W1 plus infinity, if you mod out this 1 and then truncate, you get Wn. Right. So this appears in the original AGT conjecture here. So for the SUN group, the instant partition function transform as the conformal block of Wn. So and so it turns out this GL1 has not just this one truncation. It has a family of truncation that labeled by 3 integers here. So at the level of the plane partition, is you can obtain it by having this obstruction in the center of your room. So so the corner start from here is given by this the 3 integers. So once you put this room here, I mean, you can't put the boxes. I mean, the growing of the box, the atom have to stop at this corner. So the truncation. So this also is not easy to study this truncation in terms of the W1 plus infinity base W algebra basis, but in terms of this alpha Yangian is quite transparent. So this corresponds to this instanton partition function that's given by the intersection of this. So this 2A basis, but you can think of the M5, the 3 different stack of M5 intersect. In this this is the Calabi-Yau here. So the result of this recent not so recent this paper is that for this generalized this spike instanton, this group should correspond to the truncation of this alpha Yangian GL1 by the 3 integers here. So their construction is. Yeah, I'm not familiar with this their construction. So they use this. They first use the Koha language and then do a Junifer double to get the alpha Yangian GL1. So in this paper, they also suggest that their approach should work for the general toric Calabi-Yau. I think they're working on that, how to generalize this construction to the general Calabi-Yau. Yeah, it would be interesting to know how the truncation of our alpha Yangian shed light onto this particular problem. So I mean, the goal is to classify all the possible truncations starting from the Quiver Yangian. So that's something we're currently working on. We got some truncation, but I don't think we have all the possible truncations. Yeah, but to do this, you need first you need to get all the possible truncations under control.
Okay, thank you. That sounds to be very interesting.
Can you say a bit? Oh, sorry.
Go ahead.
Yeah. Can you say a bit about the new rational vertex operator algebras? What are the supersymmetry and the central charges, for example?
Yeah, so they are not in general supersymmetric as far as I know. So here the starting point is again this. So you start from the alpha Yangian GL1. You know that is related to the UEA of the W1 plus infinity. And we know that starting from W1 plus infinity, you can get this, you can truncate to much smaller spectrum. In particular, you can get the WNK minimum model where both N and K are integers. So this will correspond to the truncation of the alpha Yangian GL1 in terms of these three integers. There's a shift symmetry here. So, okay, so I didn't explain well here. So to study this truncation, actually, Prochaska here, it's better to use this parameter that's introduced by Prochaska in 2015. So this is a, so it's an equivalent parameter to our H1, H2, H3. So it's also has this manifest S3 invariant symmetry here. So in this lambda 1, 2, 3, so this is labeled by 3. So you tune your lambda 1, 2, 3 such that it satisfies this equation. In particular, if you want a truncation, if you for arbitrary k, not necessarily integer, this just truncate to one direction. It just truncate to up to spin. And it's not rational. So you can truncate at two levels. So you have both N and K integer, then you have a rational UA. So for the Quiver Yangian, so if you look at the in terms of the gluing. So in terms of gluing, you can say I can just glue the truncated algebra. I mean, it's already, so this guy, if you truncate at both directions, then you get already a rational UA, and then I can ask how to glue them. But this is also, I mean, by definition, the glued algebra is also rational. But you can also, where's the? Yeah, you can also first truncate. You can either truncate and then glue, or you can glue and truncate. So the glued algebra is the same as this Quiver Yangian. So then the question is how to truncate this. I mean, in particular, find all the possible truncation of the Quiver Yangian. So that's something we're currently working on.
Thank you.
Yeah, in general, it's not supersymmetric, but maybe for some special cases. For example, this guy here, the resolve quantifier. This one give you an n equal to W algebra.
Do we have other questions? Maybe I can go back to the relation with the supersymmetric quantum mechanics. I'm not quite sure how that how the reduction works in that setting. How do you get, in what sense do you get a reduction to the quantum mechanics? I can see that if you have D0 branes here and you can focus on the D0 branes, then that's going to bring you down to quantum mechanics. But it's the physics of what's going on that I'm confused about.
Yeah, so I mean, basically, it's just from the point of so from point of the 4D theory, all these bound states they're just particles. So basically, I'm looking at the effective theory on the BPS particles. I mean, the word line of the zero-dimensional particles. Those are one dimension. So the D0, D2, they're wrapping cycles of the Calabi-Yau, but the physical theory we're looking at is the four dimension that's outside the Calabi-Yau.
Yes, you have a 4D, but it's being reduced to a one-dimensional one. I mean,
yes. So
are you deforming the 4D geometry in some way? Are you doing a toroidal compactification, or are you?
No. Sorry, we're just looking at the low energy effective theory because we only want to look at the BPS sector. I mean, the theory is different, but if you only want to know the information about the BPS states, the vacuum moduli of this Quiver quantum mechanics contain the entire information of the BPS particle of the 4D theory.
So there are no massless particles in this. In the end, is that what it is?
Right. I mean, we're only we're only looking at how to count this. We only want to describe the vacuum moduli. We want to just count look at the moduli space of the BPS particle of the 4D space when we're ignoring all this non-BPS part. So this is just an effective description to.
So I think it is probably equivalent to toroidal compactification, maybe. Is that what it is?
Yeah, I mean, you're just ignoring all the. You're just looking at the low energy effective theory. Yeah. I mean, so this is a right. So this is just a dimensional reduction. To your right.
Okay.
The dimensional reduction to the 0 plus 1.
Okay. All right. Thanks.
Thank you.
Are there other questions, or if not, I will. We can thank Wei Li again and our quiet format. It's very unsatisfactory, the thanks in this kind of Zoom format, but thank you very much, really, for your talk. I'm going to stop the recording and we can continue as you wish.